All right, 3/23 is today's date. I kind of find that fun. 3/23. And tomorrow will be 3/24.
Whoa.
And 3/25. So then 3/25 I like because it's got the 2, the 3, and the 5, but the 3/24 tomorrow. I like to play with numbers. So when you have the 1 in the year and the 7 in the year, you've already got 2 odd numbers. Then we get 3 is another odd number. So then if we can find a 5 somewhere for another odd number. I have had a swim coach who would only set his alarm clock to prime numbers. Like, yeah. So the number that it became had to be a prime number. I was like, that makes it very specific when you're able to wake up. He's like, I know. So, probability models are what we use to represent a situation. So we've already been working with probability models. You just haven't quite realized it yet. So when we have evenly spaced or fair trials that we're going to be performing. So spinning a spinner, this is, every region is fair, but is the probability of red the same as the probability of blue? No. But every region, if we break it up into 5 regions, is the same size, so it is fair. So we are able to use a model for this. Did we finish 16.4, by the way?
No.
We got most of the way through it, right? We only had the final last thing to talk about, and we didn't really need to talk about it, but because I see a couple people confused that we're not finishing that, so we'll talk about that really quick. So we got down to here, and we were talking about the tulips and the vase, and how that is what? Is that theoretical or experimental that you get 5 12s?
Experimental because you're taking one experiment.
So if I choose 1, and this is what concerns me because we were right at the end of class and some people pack their stuff up early. Do I really have a set of data in order to determine how many times this happened compared to how many total times? No, because I have 1. I will have either gotten the flower that I wanted, and I'd have a 100% chance, hypothetically, or I didn't get the flower that I wanted, and I have a 0% chance. But they're telling me that the probability of choosing red is 5 out of 12. Based on what? An experiment or in theory? Colin?
An experiment because it's like 5 red and 7 yellow.
So let's compare to these situations where we took 12 shots. We rolled a number cube 50 times. So we got our 3 8 times. That's how I got 8 out of 50. We got our score once. That's how I got 1 out of 12. But here, we didn't do multiple tries. We didn't pull multiple flowers. We did not run an experiment. This is actually, and I'm like almost certain, I'd like to go back and check the video, but I'm pretty sure we talked about this at the very end. That's actually theoretical. Yeah, well, we were like running out of time. But you should have this written down. If you don't, please write it down. You can write the whole word if you want. But it's theoretical because we're basing this probability off of what we see, not what we did. So we saw, but we did not try or do. So I know that's improper grammar. But we saw 5 out of 12. Not that we pulled 12 and got 5 of what we wanted. We just saw it. So that is theoretical. Questions? So check out the got it. Those 3 situations. Try that on your own for whether it's theoretical or experimental while I reorient like every day. Oh, yeah. Heads and tails. Get what they're doing there. Literally a tail. So, Moon, when you look at situation 1, an eye doctor examines 10 people, finds that 4 are colorblind, so therefore he says the probability is 4/10. What would that be?
The experiment.
He did an experiment. He looked at 10 people. Wow, that's screwed up. So this is experimental.
Year 4 is not having a good day.
It's not having a good year. John, what about a teacher chooses one student random from the class of 13 boys and 12 girls and says that the chance of a boy is 13/25.
I said that it would be theoretical because she's only choosing one.
Ah. She's making this probability based off, actually, the choosing one tells me that I did not really run an experiment. But she knows her data, right? She knows her class. 13 girls, or 13 boys, 12 girls, 25 total. This is theoretical. She's basing that off of theory that if she went to make the choices, it'd be 13/25 or 52%. What that would come out to be. And Whitney, what about you check 6 boxes of cereal and find that 1 has a prize at the bottom? Disappointing. But is that theoretical or experimental? Did you look at or did you do? You did it, right? You checked 6 boxes and you found 1. You didn't just observe, you did. So if we did it, is that experimental or theoretical? It's experimental. Any questions on those 3? Check our final one here. So we'll probably only get through 16.5 today because I did come back to finish. So class has the same number of boys as girls. Each day the teacher chooses one student at random to take attendance. School year, legally, has 180 days. How many days would you expect the teacher to choose a boy to take attendance? And, okay, we're not going to use the probability tool, but I'll show you a couple of different probability tools that you can use. So, Elena, if we have 180 school days, and like Phoenix, we're even weighted boys and girls, how many days would you expect to choose a boy?
Like half of them.
Half of them. How many is half? 90. Because if you make heads choose a girl and tails choose a boy, that's fair because you have even boys versus girls. Now, tools to model randomness.
Does the school year actually have only 180 students?
Yeah, that technically that's how many years you have to go to school. We normally budget a few extra just in case we have calamity days or things like that. But what's that going to pull up to?
That's only like 6
One
months.
website that you should throw in your back pocket is random.org. That we talked about this, I know. But it, in games, will model these random situations for you. So when I was doing my bracket, and I now realize this, is probably not advisable for first round bracket choices, but I can tell it how many coins I want to flip, and I can select a coin type. So sure, let's go Todd, Reddit, whatever, decision maker coin, and I can flip them. So these are your tails, these are your heads, or whatever you want to say. So there's do it, or, oh, well, that's kind of inappropriate. It says the hell with it. So if we go back, we can change our coins, silver or whatever. I mean, so this doesn't really matter. Use a shilling. But I'm going to get different results. Every time I flip again, it's randomizing. So some might stay the same because they have a 50% chance, but some might change. Now, if I want to dice roll, I can go to Dice Roller, and I can choose how many dice I'm rolling. If we're doing a crazy game of D&D or whatever, we might need more. Now, this is assuming 6-sided dice. We can do playing cards. We can take out certain cards. We can include certain jokers or not. And then you can set up your different situations, how many cards you want to draw from how many decks. The more decks you have, obviously, the wider out. So you could get like 8 5s, potentially, if you're using multiple decks. But if you only have one deck, you obviously only have 4 5s, because there's a 5 in every suit. So random.org is your best friend for modeling these things. And there's all kinds of stuff up here. So play around with it, check it out. It's a fun website. So now actually getting into probability models. We've actually been doing this without you realizing it. But now we're going to dig into the nitty-gritty. The biggest, most important thing here. The sum of your probabilities needs to total 1. Because that 1 is essentially what? 100%. And when I look at all of my outcomes, all of them total up to 100%. If they didn't, well, something's invalid. Because how do I not have everything totaling 100%? 100% means everything. So, when I look at the probability of red, it's got a higher probability. It's 3/5. Probability of blue, 2/5. Add them up, we get 1. Any questions? Did not think so. Wow, that screwed up at the top. So, I bet you guys can go ahead and start looking at these. So, list 1, probability of fewer than 3 shapes. So, which of these lists needs more probabilities looked at to be complete? So what you really want to check is, do the probabilities add up to 1? If not, what event have they not taken into account? So the first one's kind of easy, so I'll give this one to you guys. Like, I'll talk about it. Then 2 and 3, you're on your own. So fewer than 3 shapes, or at least 3 shapes. Well, fewer than 3 would be 1 or 2. At least 3 would be 3 or 4 or 5 or anything more. So that accommodates every possible outcome. The fewer than 3, right here to the left. 3 or more, right here to the right. 4 out of 6 reduces to 2/3. They've dealt with every situation. They have not necessarily dealt with every outcome in list 2 and list 3. So take a moment, check those out, see if you can figure out what they're missing. There you got one, Ozzy. What do you got for list 2? What are you thinking?
So for list 3,
Okay.
List 2 I didn't really find it.
It's fine. Go ahead to list 3.
In list 3, is it even number of apples, which is just taking account of all like the apple cards, and it says 1/3, but it really should be 2/3 since there's 3 apple cards.
No, wait a minute. So, probability of even numbered apples. So let's look at this, right? So, even numbered apples, I've got this one, and I've got this one. So that'd be 2 out of 6, which is where they get their 1/3. But they say even. So you're actually talking about these together. Because if we look at probability of even apples and probability of odd apples, then we're talking about all of them. So my odd apples, well, there's 1 out of 6. Now if I rethink that this was 2/6, then together I get 3/6, or a half chance that you draw a card with apples. But that doesn't account for all of my probabilities, because it would have to total up to 1. So what events, what outcomes are we missing here? Can you give me one of them? And think about things that aren't circled, events that have not been taken into account. Colin, you got any ideas of events that we haven't used in list 3?
Is the fish?
Sure.
Yeah.
Probability of a fish. What's that probability?
It would be
I've got a fish here, and I've got 4 fishies here.
So 5 out of 21.
Now, where are you getting your values at? Because
I'm all.
so don't think about number of fish. We're talking about numbers of cards that get me what I want. So this is the probability of drawing
2
a.
out of 6.
So it's 2 out of 6, or it becomes 1/3. When we add that in, well, 2 more 6 now brings my total to 5/6. I'm still not there yet. I'm still not done. So Noah, what am I still missing? Missing the leaves. So if I say probability of getting a leaf, what's that probability? How many times does leaf occur? 1 card. Yeah, it has leaves. How many total cards? Now, how many total cards? Total cards possible. So this is 1/6. When we add that in, we now get our total of 1. Now, Ozzy had said that in list 2 he didn't really find any issues. I have a major problem with list 2 because I don't know how to add those fractions. A very huge mistake that somebody, hopefully not in this class, might try to make is say that that list adds up to 1/11. You should be able to.
Add up the denominator.
Do we ever add our denominators?
Oh,
Never.
Oh, I see.
We only add numerators and can only do that if,
The denominator is
Julian, you had your hand up. The denominators have to have the common value of 6. So if I make this into a common denominator of 6, what's it become? 2/6. If I make this into a denominator of 6, what's it become? 3/6. And this is still your 1/6. Would those add up to 1? There is no issue in list 2. List 2 has taken into account every possible outcome. Any questions? Now I finally got it back. Because I keep having to like overly compensate when it's goofed up, but I got it now. Alright, try the got it. We have a robotics team. So here's our team. We range from ages 10 to 14. We've got boys and girls. And we want to talk about these 2 different probability lists. So list 1 says, oh, on the robotics team, the probability of a boy is 3/5. But that doesn't bring in the complementary situation. Now, a complementary situation, just like complementary angles, makes it nice, essentially. Like, complements are nice, right? So, a complementary situation finishes it, or, like, puts the rest of everything in there. So, if we looked at probability of boy, then, Andrew, what's going to be the complementary situation to probability of boy? If not boy, what could it be? Girl. So the complementary situation here is going to be probability of girl being chosen. And if we know that the team is only boys or girls, we don't even have to do any math or look at anything. Okay, do any math, that's a lie. We got to do a scotch of math. Sorry. But I told you that I lied, so really, I don't think it counts as a lie. What does it take for 3/5 to become 1? 2/5. And we could go back and check that. Girl, 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 girl. That would be 4 out of 10, which would reduce to 2/5. So complete list 2. Figure out what would be the complementary situation to close up all those outcomes. Take a moment. Anish, what is the other situation or other outcome that could happen here that relates to the outcomes we've already been talking about? So probability of older than 12, and what's that probability come out to be? 2/5. Or 4/10 if you wanted to leave it unreduced. But yeah, we can just look at how many people I did not get highlighted over there. There's 4 of them. 4/10 reduces to 2/5. Question? For the next one that I have not talked about yet. So you're a little bit ahead of me. I love it, but you're just a little bit ahead. We got to get down there. So, we've got a spinner, a very biased spinner. Who knows what the game is, though? That might be intentional. Like, the 5 or the yellow, like whichever one you get, which is the same, like, whether you're playing numbers or whether you're playing colors, doesn't matter. But maybe that's like the evil overlord wipes out half of the game players. And you don't want that to happen. So it's a rare occurrence. Maybe the blue is you get to advance 3 spaces. Like, we do want that to happen. That's a good one. We make that probability higher. So our action that we're going to take is obviously spinning. Can't roll the spinner. Makes things difficult. I mean, you could, I guess. Each of the 8 sectors is an outcome. So we have probability of red, probability of odd, probability of yellow. No thoughts yet? Monica, what are your thoughts here?
It's missing the blue. And even. That is
So-
yellow, right? The 5 is a yellow. Or is it green?
Yellow. Yeah, if they're saying yellow, that must be yellow, but it is kind of a weird yellow-green. Kind of baby pink.
Then it's missing blue and even.
So, you're saying we're missing blue and even. So if I look at blue, well, there's 4 of those regions, so I get about a half. If I look at even, well, there's 4 of those regions, so I get... Now, if I add all these up, though, I'm supposed to equal 1. But these already equal 1.
Oh, wait.
Dom, I'm curious what you're thinking. No, I'm curious what you're thinking.
No, I had an idea. Now I'm saying it.
What's your idea?
Okay, well, I was thinking that we would have to convert them into 8s because the spinner's an 8.
It still won't work out right. That would make it easier to look at, but it still doesn't work out right. Andrew, what's broken
I
here?
have no idea what's gonna happen, but like, it all ends up, if you do every single one, it's gonna end up being 2. So we're probably either gonna have to combine some or like add. Because maybe you have to look at the
Sean, we haven't talked yet today.
get rid of like yellow and red, just didn't even know.
So, I kind of agree with that. Julian?
You have to add them up separately, odds and evens and colors.
We need lists that have related outcomes. I don't want to look at the probability of spinning a red and then compare that with the probability of spinning an odd because they overlap. So I can't have overlap in the events that I'm discussing if I'm trying to create a strict model. Now, when you get up into like high school math and you're dealing with compound probabilities and we have overlapping events, things get a bit different there. But with the models that we're going to start with right now, we need our events to be very specific. So, make 2 lists. Let's make one list that deals with color. Let's make another list that deals then with, what would you say?
Type of number?
Numbers, right? The hashtag symbol means numbers. It also means pound. It is not just for Insta thingings.
Snapagram and
Snap a booking. So, if I'm going to do colors, they already told us the probability of red is 3/8. We've been also told that the probability of yellow is 1/8. What color has not been accounted for? The blue, which we determined is 1/2. For numbers, well, they started with odd. So since they gave me odd, then my only choice for my other probability is even. And that's also 1/2. So if this was the spinner that came with the game, but it was a make your own game kit, depending on what outcomes you want to force, you could either create evenly chanced outcomes. Spin an even number, this happens. Spin an odd number, that happens. Or you could make weighted outcomes, least likely, more likely, most likely. Does this make sense? So, this is also where some games use things in two different ways. You could use the same spinner, but maybe when you pick up the card, it tells you whether you're spinning for color or spinning for number, and then what happens. So, lots of game theory takes into, actually pretty much all game theory takes into account the probability. I did not, I worked last night, dude. I had no time to look it up.
You should look at right now.
If you're really
I did. I will say I have a huge bias. I'm very, very hopeful that we will get. I'm hopeful that the lottery will pull this one student that's been coming to climb at the wall. This is hilarious because I would see it happening to any of you guys. We're standing there and we're climbing, and she's in 6th grade, right? But she looks like a little bit older, but she doesn't look that old. And I'm belaying for somebody, and this woman walks over and she looks at Naya. I don't know if any of you guys, I forget her last name, but she looks at Naya and she goes, "Did we talk to you about getting somebody to belay for us?" And Naya's like, "I'm 12. I don't work here." Like, this woman thought that Naya was apparently an employee at the wall because we were just like chatting, like really casually. So she thought she was an employee. So I thought that was very funny. Like, you're a bad judge of age. Huh? Because she's awesome. She would fit in at Phoenix very well.
Oh,
She's applied to Phoenix. Like, no, she's a 6th grader trying to get into Phoenix. She would be great. Yeah, Andrew's with me. He's the only one awake this morning. All right, so a probability model based on theoretical probability of equally likely outcomes. So please highlight, if it's equally likely outcomes, this creates what we call uniform probability. So a coin flip is a uniform probability model. Equally likely outcomes. A dice roll is, well, a die roll is a uniform probability. What about rolling 2 dice? Is the sum, if we're summing, like we normally do with 2 dice, are the sum outcomes equally likely?
No, because there are multiple ways you can get the same number.
Yeah, well, and some numbers that you can only get one way. So, multiple dice, if we're summing, is not a uniform
I
probability.
think you can never get a 1 on a 2 dice.
Correct, if you're summing, yeah. Now, if you're multiplying the dice together, because there's fun dice game where you can do different math with them, then you can
Or
get
if
1.
one of the dice has an empty side.
Right, yeah, and there are some dice games that use that as well. Empty-sided dice. Like, you only want it to have, like, a 1, 2, 3. So then the other sides are just, like, 1.
Or a 1, 3, 5.
Right, yeah. So, here's what you need to think about when you're determining, and if you've done your 16-3-4 homework, you've already kind of had to start thinking like this. Do I need to use collected data, or can I use theoretical probability because they're equally likely? Because I know, like, I can just do the math and figure out the probability. So, city planner wants to know the probability that a car waiting at the stop sign will turn left, go straight, or turn right.
Why?
Because they're programming the stoplight. I knew you were going to be the person to ask why. All stoplights have a computer program running in them, unless you go to a podunk town, and they're just set for like 30 seconds each. And then people get frustrated, because they're sitting there, like, there's no traffic. There's no traffic. There's no traffic. Why aren't you changing? There's actually now a law in Ohio that you can run the red light.
Yes.
If it is after a certain time at night, I forget what time it is, so look it up if you want to know. If it's after a certain time at night, and you're waiting at a red light, and you've already waited a certain amount of time, and there is no traffic coming, you can reasonably cross the intersection safely, you are allowed to run the red light.
Yes.
Because of computer programs that operate the stoplights not always working as effectively as they should.
How are they programmed?
So actually, Sawmill is a really good example of this. So Sawmill, pretty heavy traffic up and down, north to south. Depending on whether it's morning or evening, depends on how the traffic is flowing heavier. Certain times it flows north heavier, certain times it flows south heavier. So if you sat out there all day long and timed how long green went north and south versus east and west, and then kept track of all of those, how much the turning lanes got, how much just straight traffic got, you would see trends in the data of when traffic is flowing heavier north, the green light stays on longer heading north.
So somebody calculated the probability and then inputted that into.
So you'll occasionally, when you're like driving around, and you'll notice this more as you get your license, you'll see a guy at the box over to at the corner switching the light, manually switching the light and writing down all the data. Because what he's doing is waiting for enough traffic to stack up that we need to switch the light now. And then he documents how long that took. And then he lets the light go until traffic stacks up the other way. He switches the light, writes down how long that took. Eventually, with enough data collection, we can create a program that will run based on the averages of those times. And most of them have weight sensors too. The weight sensor can trump the computer program.
What's the weight sensor?
Like in the ground, it senses when a car is on top of it.
Wasn't it for like a trolley at one point or something?
Not certain.
So
Okay,
basically,
I mean,
if a lot of cars are waiting and there are no cars like waiting on the going on the.
There's a lot of details to that law. Like if it's the middle of the night and you're sitting at a red light and you've already been waiting, I think it's like 30 seconds or something like that, and the light's not changing and there's no cars coming, you can go. Like, and you can turn right on red at most places, but this is like you could go straight through the intersection. Or you could turn left if there's no cars coming and you can do it safely. That's a new law that was introduced this year for Ohio. So, two friends on a walk are playing a game. These are two different situations, so we're going to talk about both of these. At each intersection, they choose at random from 3 slips of paper. So a paper and a hat, they're choosing at random. What's the probability they will turn left, go straight, or turn right? So how does situation A and situation B, how are they different from each other? If we're talking about probability of turning left, or going straight, or turning right, which one do you think is easier to discuss?
B.
So Monica said B. Anyone agree with B? B is easier to think about. We're just pulling slips of paper at random. Anyone think A is easier to think about? We're determining where traffic is going to go. So Monica said, we look at B. Let's say you were playing this game. What do you think the probability of going straight is?
A third.
What do you think the probability of going left is?
A third.
And right?
Third.
How do you know that?
Because there are 3 options and if you, yeah,
And those options are...
straight left and right. Oh, they have equally likely outcomes.
Those 3 options here have equally likely chances of being drawn. You are randomly from a hat picking them out. They all have an equal chance.
Does that mean simple random sampling is uniform probability?
It can be yes. So if every outcome only has one slip of paper or number or whatever we're using, then that creates uniform probability in our simple random sample. Yes. So you're going to talk about situation A?
No, I just still have to do that.
Okay.
Would, like, turning left be less likely? Because not many people like to turn left.
Why? Hold on. Shh.
'Cause,
Don't
like,
shoot him down.
Because most people, because it's just a pain in the butt to get through, like, 2 sides of cars coming. And most people just like to take rights and go straight.
UPS has what's called I forget what it's actually called, but I call it the right turn algorithm. UPS drivers are not allowed to turn left.
What's these things, John?
You're not a parcel service or something. It's delivery trucks for
Wait, how
packages.
does your GPS get left on the street?
So, how could you not ever turn left, Ellie?
3 right, single left.
3 rights. So, what they did is they, over time, tracked data. And they said, how long do we waste waiting to turn left? Because if there's traffic coming this way, you're waiting for that traffic. If say this was a stoplight, if the light doesn't have a left turn arrow, you're waiting till the end of that cycle so you can slip in your left turn right when the light turns red. But if there's any cars in front of you, you're waiting for the next light cycle where hopefully you get to turn left. So, UPS essentially had a bunch of drivers go out and drive like normal. Left turns, right turns, whatever. Then they had a set of drivers go out, and if you were gonna make a left turn, let's say you were gonna turn left here, you'd go past it, turn right, turn right, turn right, and then you'd end up going where you need to go. What they discovered, making 3 right turns and driving further than you need to is more efficient than making a left turn. So now it is company policy that they do not make left turns. It is also safer because you're never crossing opposite lanes of traffic except going through an intersection like this, which the other traffic should be stopped. If I go turn left, I'm going across inbound traffic. If I don't see them and they hit my truck full of packages, that's no bueno. No good. Ozzy?
But I've seen UPS drivers take lefts through my neighborhood.
Yeah, I forget if it's UPS or FedEx or one of those things. But that doesn't mean that they all stick to it. And if they're in a neighborhood, that's different than if they're out in a traffic grid. So this is more so for like in cities and like gridded roadways. So the problem with Worthington especially is our neighborhoods are very pocketed. You can't make multiple right turns and get where you need to go. You literally sometimes have to make a left turn. So that's where the fault comes in. But if you think of like New York City, it's all grid, right? So I'm going to make 3 right turns instead of turning left. So that's where that plays in. Oh, so what we're really saying also here, and we're talking too much today, but especially since you guys have a test tomorrow, I'm not really like... Some days we just want to discuss the math so you guys understand it. If we're talking about the probability of cars turning left, somebody already mentioned they're probably less likely to turn left.
That's me.
But then, if we think about probability of going straight, or probability of going right, what would determine where the cars are going?
Where they want to go.
Sam?
Their location.
Yeah. What is straight? What is right? What is left? If left is a single neighborhood, probably not that many people are going to go there. But if straight is Kroger, probably lots of people are going there. And if right is the way to get to 270, probably how most people get to work. So you got to know what's going on here. So this will not be uniform because we don't know that there are equally likely chances. We can actually almost guarantee that it won't be equally likely. Now, we don't know until we collect data. But because it's not uniform, we would need data. So when it's not uniform, we would need
So
data.
you can only do theoretical probability when you
Equally
don't...
likely outcomes.
Yeah.
Dom?
Wait, okay, so on the UPS or FedEx policy where they go into right, so what if on this, they need to take a left and they can't because further up, what if there was no road to the right so they couldn't do 3 rights?
Yeah, they route that. So logistics is essentially the science of routing things and getting things where they need to be. So they've got people that determine that. Yeah. So they would set your route to be most efficient. For which situation could you use uniform probability? You drop a thumbtack from a height of a foot. What's the probability the thumbtack will land point up? And this color cube has 2 red faces, 4 yellow faces. What's the probability of getting a yellow face? Now, this is where misconceptions come in. Uniform probability does not mean that the events have equally likely outcomes. It means that the thing we're using to create the outcomes has predictable or uniform or fair probability. Can you ever drop a thumbtack?
Yeah.
You know, or anything and figure out if it lands up or down? Is there a way to know mathematically the chance of it being point up or laying down?
It's 50-50.
No,
I highly doubt it,
Why?
because weight. Think about it. This is not a uniform object. You're not dropping a quarter where it's got two choices and they're even choices. This part's heavier, but this part's pointy. So if it falls and the point kind of hits the ground, it's probably going to get stuck in the ground. If it falls and bounces, it's probably going to land like this, but we don't know what those chances are because it's not a uniform object. So this, we would need data. Could you predict the probability of red here? What would it be? And the fact that you can quickly say that the probability of red would be 2/6 means that this is a uniform situation. That doesn't matter. So that's what I was just saying. Uniform probability doesn't mean that every, so where this is uniform is every face
Oh, every
is
face
1/6.
has an equal
But red versus yellow does not need to be the same probability. It's that every face that determines the outcomes. So this, we can theoretically figure out our probability. The thumbtack, we can't really. And we're just going to skip the last one because it doesn't matter. So Monday or whenever we end up on it, we will finish up the 16th chapter and figure out when we take that mastery. Thank you guys. Have a wonderful day.